Okay, question 5, quarks and leptons. So we have to describe the interaction that is responsible for keeping protons and neutrons together in a stable nucleus. We need to know straight away this is the strong interaction that keeps us all together, and really we're just describing various properties of the strong interaction. So marking points might include it has a short range. It's only really felt at about 5 centimetres. Anything beyond that is negligible. It pretty much doesn't exist. Once we get under 5 centimetres, it's attractive, and it can overcome the electrostatic repulsion. But once we get to about 1 femtometre, it becomes repulsive. And this is why they're relatively stable, because you have an attractive force and a repulsive force, so it kind of just sits around there. Very stable. Other things you might want to say is it only affects one type of particle, and that is of course hadrons. Leptons do not feel or experience the strong nuclear force. Right, part B. Just open a new one. Okay, part B. Nuclei can decay by alpha and beta decay. In alpha decay, only one particle is emitted, but in beta decay, there are 2 emitted particles. Explain how baryon number is conserved in alpha and beta decay. So, there's various ways we can do this. We'll do alpha first. Should be relatively easy. If I have let's say Z is my proton number and A is my nucleon number, my mass number, and let's say it's going to go to a different element, then basically we're going to have Z minus 2, because we're going to lose 2 protons, and A minus 4, and we're going to get a helium nucleus for 2. But basically, the total baryon number is unchanged.
Mommy, what's this on the stool?
That's the pencil.
Huh? I did.
So baryon number remains the same in alpha decay. Beta decay is a little bit harder. So in beta decay, we're going from some element X into some element Y. This time we're going to add a proton, because a neutron turns into a proton, and we're going to emit a electron and an anti-electron neutrino. This diagram by itself will be fine. It shows that baryon number is conserved still, because the total nucleons A and A remain unchanged, and that's the neutrons and protons both have a baryon number of 1, so that's also conserved. The electron, the baryon number is nothing, because it's a lepton, as the anti-electron neutrino also has a baryon number of nothing as well. Right, next bit. So part C. Kaons are mesons that can be produced by the strong interaction between pions and protons. The equation shows a reaction in which a kaon and a lambda particle are produced. So we have this pion with a proton going to a meson and some mystery particle, lambda particle, which you probably won't have heard of, but there's many different types. And we need to find the quark structure of this guy here. So it might be worth us writing out what we know. A pi minus, we should know this to be an anti-up-down configuration. It's a meson, quark-antiquark pair. You can work it out from that hexagonal diagram, or we can just learn that. Proton, we definitely should know that's up, up, down. And the K meson is a down anti-strange. Remember, kaons have strangeness, which is really, really important. Right, so it must be a baryon, because to conserve baryon number, you've got a +1 here. This one doesn't have any baryon number, it's not a baryon, so it must be a baryon number of +1, i.e. it must be 3 quarks, or antiquarks, or whatever. Its charge must be 0, because we've got a 0 charge there, and we've got a 0 charge here, so the whole thing is uncharged. So that kind of narrows our options. Now it does say in the question that it's a strong interaction, which is a real clue. That means that strangeness has to be conserved. So we've got our K0, which is a down anti-strange particle. So that means that we must have in our quark configuration here, one of them must be a strange particle. And the strange particle has a charge of minus a third. So that gives us a clue. The total charge must be 0. We know we've got strangeness, which is a minus a third. So I need 2 other configurations of up or down quarks that are going to give me basically plus a third in total, so it all cancels out. And the only possible solution for that would be an up quark with 2/3 charge and a down quark with minus a third charge. That means that charge would be 0, and that would fit. So our answer, SUD, strange up and down quark. Okay, moving on to part D. We've got a kaon decaying by the weak interaction. So K0, which has strangeness, going to 2 pions, a plus and a negatively charged meson. One feature of this decay that shows us the weak interaction, while the kaon has a strangeness, these two don't. So strangeness is not conserved, therefore must be a weak interaction. So your answer, strangeness not conserved. And finally, we've got part E. It's one of those wishy-washy sorts of questions. There have been considerable advances in our understanding of particle physics in the past 100 years. Why is it necessary for many teams of scientists and engineers to collaborate in order to these advances to be made? Can't escape the learning habits. So first of all, your results need to be validated. You can't just have one person or one team doing this. They must be checked by other different teams to make sure they are correct. It's just how science works. There's other advantages as well. Particle accelerators are not cheap, so having lots of people work together and spreading the costs. It's a very complicated process, the design and engineering of them, so you need lots of different disciplines. Many different skills are required in order to get the results that you want. And another thing you could say is these experiments are run billions of times, so it generates lots of data, which will be very difficult for one team to analyse. So you can spread the data cost around as well. And that is it for question 5.